Okay. Well, so today we'll be talking about balance trees. Yeah, so it's discussion 5. So welcome everyone. Let's get started. So first and foremost, tips session number 2. So if you didn't choose to replace the higher legator quiz with tips on the spreadsheet, then you have to do the higher legator. I mean, you're still allowed to go to this, but you can't replace it. You can't replace it with the 4 quiz, the higher legator quiz. But yeah, the second session is tomorrow, I think. Yeah, tomorrow at 6. So yeah, you guys can all go to that. That'll be pretty interesting because it's actually a panel of people. So I think it's a good opportunity to kind of learn what interviewing is like at different companies. All right, so that's that. But okay, so moving on. So yeah, for today, our objectives are first, we're going to do a project review. So we're just briefly going over the project because today we're going to talk about balance trees anyway. And well, probably one is on ABL tree, which is a balance tree. At the end, we're going to do the quiz question review. We're not going to do it too. We're going to after the coding question, but we'll get to it. And then we'll talk about trees, so balanced, red, black, split, and B+ trees and B trees. I think the most important ones for us are like balanced trees and then B/B+ trees. But we'll get into that later. So then so first of all, project 1 is Gator AVL project. So you're going to implement a custom AVL tree. That says here. And I guess you guys, if you read the directions, you might know that. So you're going to be doing like insertion, remove, search, traversals. But you also need to implement rotations. I think you only have 2 rotations, I think, on insertion, but oh yeah, here actually it does say that. Because on deletion it's more difficult. But these are the 4 things you're gonna have to do. But hopefully after today, if you guys don't right now, do that. Okay. So what do you have to do for the project? You have to design the interface, functions, all that. You have to parse the input. And then you have to build your main in order to parse that input. And then you have to call functions and test your code. And you're going to have to write your own tests, or some of your own tests. I think we've read some, but not all. So it's a good opportunity for you to learn about writing tests. That's good for that. Okay, well, go for grading. So for grading, 25 points of implementation, 15 points of documentation. So yeah, basically just this, like the rubric, I would say. You have to know how to, if you do all this, then you should be fine. There is bonus if you create your own test cases, so that's good. You don't if you're not going to get 100 bonus points, can really help. Okay. So now on to there's more. Okay. Project one breakdown. So yeah, there is a presentation. I suggest looking at this actually if you haven't started the project already. It is a really good intro to kind of get an idea of how to start the project. So these are slides for it. This is the link to the recording. So yeah, I do highly recommend you. So now we're going to talk about balance trees. So you might be thinking to yourself, why balance trees? Why even bother? We've already talked about binary search trees. We're good, right? Well, there is a use for them. And the use for them is that if no tree is balanced, we talked about last week actually. You guys remember about complete trees, right? And complete trees are a type of balanced tree. And if you remember, we proved in class or in discussion that the height of a complete tree is bounded by log n, right? And the only thing we used about complete trees to determine the height was basically the fact that it's balanced. So the fact that everything is at the same level. And as a result, the same is going to be true of balanced trees. The balanced trees, the height of a balanced tree, the whole idea is that it's going to be limited by log n. So because the height of the balanced tree is log n, then searching, insertion, and deletion are also going to be log n because you only have to go through full log n levels. In order to, like if you want to find any node in the tree, it's binary search tree, right? So you can go left or right at each node, and the height is only log n, so you only have to go through log n. And yeah, that. So for a regular binary search tree, insertion and deletion have average time complexity of log n, but it might be worse. Like we might still have a tree that's just like a linked list. Everything's on one side of the tree. But the worst case, so the worst case is n, right? And this is if the tree is unbalanced. So that's why we care about balanced trees, because they give us really nice searching and searching. Yeah, that's the question. Yeah, so just to draw what I meant by that. So, by linked list, I meant like if you have a tree, and like your tree can have something like this, where you have like no left nodes, right? So really, that's kind of just a linked list. So what do we mean by balance? So the way we're going to calculate balance in this class is the height of the left subtree minus the height of the right subtree. So the way we calculate balance value is called the balance factor. So take a node, get the height of both its left and its right subtrees, and you subtract the height of one from the other, and do height of left minus height of right. It doesn't matter whether it's one way or the other, because you're just going to get, all we care about is the magnitude, like whether it's like -6 or +6, right? But for the sake of this class, I think we're just going to do left minus right. And yeah, so here we're going to do left minus right. But the way we calculate it, right, is we look here. Node 1 in this example has a balance factor of -6 because we have height of left from the root. We'll just look at the root first, right? From the root, the height of the left subtree is 0, and the height of the right subtree is 6. So we have 0 minus 6 is -6. So can someone tell me what the balance factor of this node is? 2. Yeah, exactly. This is -2. Exactly right. Because the height of the left subtree for this node is 0, and the height of the right subtree is 2. So 2 minus 2 is 2. And on this one, every node has a balance factor. Well, of what? 0. Exactly. Awesome. Okay. So let's move on from this. Hopefully that makes sense. And okay, let's talk about insert for balanced binary search tree. So in the nice thing is the average time complexity and the worst time complexity are both log n for balanced binary tree, binary search tree, or balanced binary tree in general. Well, I guess it'd be, yeah, you have to use the search property, so you have balanced binary search. So every node in a balanced binary search tree has a balance factor that's -1, 0, or 1, and that's how we use that. Like, that's how we are able to keep it balanced, is that you always have to have balance factors that are -1, 0, or 1. If it's not one of those, then it's not going, at least for ABL trees, it's not going to be a balanced binary search tree. So that's how we maintain the property, because at every level, like the height of the left and height of right differ by at most 1. So balance factor is the difference between the heights of the left and the right, as we mentioned. And this is how we always travel the minimum amount of nodes to get to a target. And it's logarithmic growth, because basically we're saying that at any node, the height of the left and height of the right are like evenly split. That's what I mean by balance. Like there's a good balance between them. So on this, we go back, like this is balanced, right? Because for every node, left and right are kind of balanced out. And so we'll look at some examples. So maybe this is hopefully making some sense, but if not, it's okay. So notice, like we mentioned, or like we saw a few slides ago, these are the same trees. This is an unbalanced tree, and it's unbalanced because, again, height of left and height of right are at most, well, a difference of, like the difference between height of left and height of right for some nodes is greater than or equal to 2. There's a magnitude, and this one it's not. So just like looking at what it would take, we wanted to like search for a node. So if we wanted to look for 7 in this left one, notice we have to traverse 7 things. 1, 2, 3, 4, 5, 6, all the way to get 7. But in the right one, when we get 7, well, because it's balanced, we go 4, 6, and then 7. And as the tree scales up larger and larger, on the left subtree, you're gonna have to look at more and more nodes, but on the right subtree, it will not grow as fast. In terms of, okay, so what about rotations? We mentioned rotations, they're a key component of balanced binary search trees, or self-balancing binary search trees. So what are they? Well, they move around nodes in a binary search tree without violating its property. So this allows us to maintain like this -1, 0, and 1 property they mentioned here. Yeah. This is going to be true because of our rotations. So this is what makes it balanced. There are 4 types of rotations based on the type of imbalance. We have left, we have right, left, right, we have right, left. Those are 4 types of rotation. Okay. And all of these should have O1 time, which is really nice because what that means is that balanced binary tree or balanced binary search tree, well, at least to perform one rotation, just takes O1 time. So after an insertion, it only takes O1 time to fix the tree. And we'll mention deletion later, but that's not so important, especially for your project, because you only have to do like only rotate on insertion. But for the right, okay, so let's talk about left rotation first. So for left rotation, what you do is, this is what we call right case, because you have some node that has an imbalance. So the trick for balancing a binary search tree is you find a node which is imbalanced. So in this example, let's say this is your whole tree. Can anyone tell me which node imbalances that? Yeah, the first one, right? 1, exactly. Because this one has, well, 0, -2, -2, right? So this node is imbalanced. So this is where we need to perform our rotation. And in this case, we call it a right case, because the imbalance comes from the fact that it has a right child, which has a right child, and there aren't other children to balance it out. So this is where why we need to rotate. And the way we do that, we fix a right rotation, or the way we fix a right imbalance is we do a left rotation. And you can kind of see with this gray arrow here what that looks like. So we rotate left around the one in the middle. So right, like you can kind of think of it as like, if you have like 3 balls and like a piece of yarn, if they're in order like this and you pick up the middle one, the other 2 will kind of, I don't know, kind of fall into place. So you can kind of think of it. That's how I usually like to think of it. Is I like think, okay, if I pick up the 2, just like hold it up, and the other 2 fall into place to the left and to the right. And what we notice is that actually gives us exactly the right kind of tree. Because we have a 2 is the root, and 1 is the left child, and 3 is the right child. And that's balanced, right? So yeah, that's how we handle a right. Okay, so you might be thinking, all right, so it's probably the same, but flipped for the left case, right? And you'd be right, it is. So for left case, these perform a right rotation. So left, right rotation, right, left rotation. And in this one, it's the same idea. Have an imbalance of 3. So your right rotation, so you get the middle node over to the top, and the other 2 fall in place. And that's it. Okay. So we have 2 other kinds of rotations we're going to mention. Remember, we mentioned that there's a left-right rotation and a right-left rotation. So first, let's do left-right. There's already an arrow here, so you can see there's another slide or another part of the slide. But for the left-right, if there's a left-right imbalance, that means that the imbalance comes from the fact that there's a node which has a left child, which then has a right child, and that's where the imbalance is at. So you have a difference of 2 between, like, on the left side, left subtree, there's a height of 2, and on the right subtree, there's a height of 0. And so that's when we call left-right imbalance, when that left subtree has to go left and then you go right. So you have a left-right case, and for left-right, you fix it using a left-right rotation. And as the name suggests, that's just a left rotation followed by a right rotation. So yeah, so for a left-right rotation, first thing we do is we perform a left rotation. That's what we see on the left here. And what you're really doing is you're like you're basically moving like the 2 up to where the 1 is. So I think for me, this one's a little harder to see visually. So when I see this case, I kind of am like, okay, what would it take to fix this? And sometimes like I just have to look at the whole thing to see the end goal, because this is the end goal, right? So if you see something like this, where you have an imbalance, and it's like 3, 1, 2, right? Maybe like the way I do it is I usually just think to myself, okay, how can I arrange these numbers to make it balanced? So you want to put the middle number of these 3, you put the middle number as the root, larger number to the right, and smaller one to the left. And it's balanced. But the way we actually do that is with left-right rotation. it looks like this. First, you rotate left on the middle one. So this 2 and 1 kind of swap spots, and then you have a simple one, right? After that, we have a rotation we've already seen before. We're basically trying to turn it into a left case. And then once we're there, well, we just perform what kind of rotation to go from left to balanced? Right, exactly, yeah, right rotation. And that's it. So we, yeah, because if you notice at the end, like this 3, right, is still at the root after the first rotation. So for this one, we kind of just have to like swap the 2 and the 1 sort of. Like you are rotating, but you're like rotating the 2 up towards where the 1 is and the 1 is down. Yes. Okay, that's the left right rotation. And now we'll talk about the right left rotation. So right left rotation is just the inverse of the previous slide. We saw left right, now we see right left. So the right left case is when you have a node, and then the imbalance is because you have something on the right and then something on the left. Right. And the way we fix that is the opposite of what we did before. First we perform a right rotation, then we perform a left rotation. And again, like how I usually look at this is same as before. I see 3 nodes, I'm like, okay, how would this be balanced? I take the middle one, take the larger one, take the smaller one, and it's balanced, right? But of course, it's not always that simple, so it's good to know the rotations as well. And the way we do that is, again, we rotate the 2 and the 3, so the bottom 2, and you kind of just swap their spots. And then after that, you have a right case, and so you just perform left rotation. So these are kind of rotations. And rotations are a little bit tricky, I'll admit. They're not so easy. So first, so hopefully it makes some sense, but you guys will definitely get some more hands-on experience with your project. So these are the rotations. So just a table that summarizes it. When do we use each type of rotation? So left is when you have a balance factor of 2 on the parent and 1 on the child. And you might be thinking, okay, what does that mean? Well, if you remember, that means that it's 2 more on the left than on the right, and 1 more on the left than the right for the child. That means you have 1 more or 2 more on the left, and for the child it's 1 more on the left. So this is the left case. So +2 + 1 is left. So perform right. But I wouldn't worry like too much about the numbers. Like the numbers are helpful, especially if you're writing code. If it's something more visual, like maybe like for example on a quiz or something like that, then just knowing like if you can recognize the rotation based on the name, that's also good. And then like the rotation that's necessary, so the imbalance in the rotation. Yeah. Child. Yeah, it's going to be based on the child and the parent of the child. So as you're going through it, right, you're going to have balance factor parent, and then you're going to have balance factor your child. And these are your 4 cases for imbalance. And then this table will pretty much be gone. Okay. All right, so we'll have a poll question, our first poll question. And so when implementing, so go to this, go to Menti and use this code. Hopefully, so yeah, they're not on yet. We'll go ahead and start it. Yeah, so which of these answer? So go ahead. If you can't see online, it says for the left subtree 4, 6, and 8 in the
When working with rotations at like a bigger scale, is the idea to like work from the bottom up then?
So yes, that's right. Like the thing is that you'll notice that there's some sort of imbalance when you insert or delete only. So you do it right from the bottom, so where it happened. So the nice thing is that on insertion, it can be at most one rotation happens. Okay. That's not true for delete, but you guys don't have to.
Okay, so thank you.
So I see some explanations, so we'll go over this one. So for this question, for the left subtree, that balances it for 4, 6, and 8. Well, we notice here that 8 is imbalanced, right? And well, the type of imbalance is left, left. So that's this one, right? And the left, left, we fix it with the right. Answer should be C. And we can write the balance factors. 2, 1, 0. Okay, so now question 2. Let me reset the minutes. Oh, whoops, didn't. Okay, now you guys should be able to do that. And it says your mind, it says for the right subtree 14, 11, 12. That's the part that's about. So I'm seeing good answers. Yeah, so for those who've answered already, awesome. We'll go over this one as well. This is a left, right rotation, or imbalance, right? And so it's right, it's left, right. And so we perform a left, right rotation. Okay, so how do we perform the rotation? Let's perform the rotation. So notice our balance factors 2, 1, and 0. So we're going to do that, right? Is again if we have in this case a left, left, we just perform a right rotation. So like this. And that's it. It's just one rotation. We move the 12 up, the 14 to be its right child, and the 11 to be its left child. And now it's balanced. Okay. And now for this one, what rotations does this tree need? Well, this one's a little bit tricky, so I'm going to go over it a little bit. So what we notice is that the rotation is necessary that you have, well, first we need to figure out balance, right? So at the root, right, the height of the left is 2 and the height of the right is 2. So 2 minus 2 is 0. And for this 5 here, we have height of left minus height of right is 1. And for 17, height of left minus height of right, negative 1. But at 2 and 25 is 0. So are there any imbalances? No, right. Awesome. Yeah, no imbalances. So we don't need any rotation. All right, so that's question 3. Yeah, none. Okay, so another question. Oh, where is it? Okay, so we'll go over this one as well. So what we can see in this one is for A, right? You have this node is imbalanced A, right? And the imbalance comes from the fact that you go right, left. So the imbalance is a right, left imbalance, but the rotation for right, left imbalance is also right, left, right? So A, right, left. And then for B, it's a right, right imbalance. So we perform a left rotation. So the answer should be for question 5. I think this is probably the last one for a while. Which is good because I'm not sure. So what's the worst case complexity concerning this tree? And I guess there are kind of two right answers, but hopefully you kind of get the idea of what's. I guess there's another full question on the next page, but. Okay, awesome. Yeah, I'm seeing a lot of right answers, which is good. I think everyone's answered this correctly. And so for this one, well, is this tree balanced? No, right. What do we know about balanced trees? Well, we know this. It's unbalanced. The worst case for insertion is you have to iterate through all of the elements. And so the worst case is D, no event. And yeah, keep in mind that worst case complexity for searching and deletion in a balanced tree is also that. Why does it keep switching? Trying to escape the other one. So next, Menti is this. What's the worst case complexity of inserting into this tree? Or I guess searching in this binary tree. I think we need to answer this time. But I want to make sure we have time for the rest of the slides because there's some important stuff in there. So for this one, the answer is going to be login. And the reason why it's login is because we notice that this tree is a balanced tree, right? The height of the left minus height of right on 2 is -1, right? So -1 here, 0 here, 0 here, 0 here, and 0 here. So this tree is balanced. And so for balanced trees, worst case, search, insert, delete, all login. And the average is login. Okay, so ABL trees, these are a type of balanced tree, or type of balanced binary search tree. So one thing I want to make clear about ABL trees is like, this is a type of balanced binary search tree. So if I gave you an ABL tree and it wasn't a binary search tree, or if I gave you a tree, right, and it looked like it was balanced and everything, but it's not a binary search tree, can it be an ABL tree? No, right, exactly. So that's something that's good to know, right? It's only an ABL tree if it's a binary search tree also, even if it's balanced. Okay, but it's self-balancing binary search tree. And really it's pretty much what we've been talking about today with the rotations are primarily for ABL trees. There are also rotations that are necessary for other kinds of trees, but yeah, the ones we're talking about today are most applicable to ABL trees. So yeah, every node has a height or a balance attribute, and we can update it on insertion and deletion. And yeah, after each insertion, at most 101 rotation happens. After each deletion, at most log n rotations happen. So what this means is that really, when we insert, you only have to do like one rotation, and that's it. That's why we only make you do insertions for a project. For deletions, it can be a little bit different because, like, you could have a problem where it's almost like a perfect binary tree, but then maybe you have one off to the side on the left, but then you remove the thing all the way to the right, and then it has to go all the way up balancing. But like, don't worry about that, really the takeaway from this is like when you insert at most just like one rotation happens. Yeah.
Is that capital N for like height of the tree,
Uh,
or is that like?
N is the number of nodes in the tree.
Okay.
Good question. Okay, and yeah, since it stays balanced, the nice thing is for ABL trees, insertion, deletion, and searching are all again. Okay. And all elements should have a balance factor of -1 or 1, 0, 1. And so let's look at insertion and adjustment example. So for original balanced ABL tree, you have 2, 1, 3, 4. This is balanced, right? And then we insert a 6, right? So since we inserted a 6, like after inserting the 6, it's like you mentioned earlier, Tyler, where you go back up towards the root until you find the imbalance. In this case, that's exactly what we have, right? We add actually it's 5, sorry. We add the 5, and then we go back up, and we're like, oh, imbalance is here. And then we perform our rotation, and this is what kind of rotation do we need here? Right, a left rotation, awesome. And so we perform our left rotation, and it becomes a balanced tree again, like we see here. Yes, exactly. If the balance factor's magnitude is greater than or equal to 2, right, then we have an imbalance. And so we insert 5, right, and then the tree iterates through the nodes, pass on the way to insert, check if it is balanced, so it goes back up, and then it performs the left rotation, and then the tree is going to stay balanced. And for an ABL tree, yeah, if you have to, I noticed last week there was one quiz question that asked you like insert elements into like a binary search tree, and like I don't know, I think a lot of you got it, but for those who didn't, I just wanted to kind of go over that so briefly, because with an ABL tree it's similar to the rotations, but for example, if I asked you to insert like 2, 4, 5, 6, something like that into a binary search tree. I just wanted to go over an example of that because it was a quiz question last week. I noticed like some people got it wrong, so I wanted to make sure that was a question I saw. Larger percentage of people got wrong, so I wanted to go over that in particular. So we would do that, right? Is we have 2 is the original root. We insert 4. So 4 is larger than 2, so it's going to be the right child 2. And then 5 is larger than 4, so it's the right child 4. And 6 larger than 2, so it's going to be the right subtree. Larger than 4 in the right subtree, larger than 5 in the right subtree. So it's going to be like this. Notice that for an ABL tree, after inserting which element, we would need to rebalance when inserting these into. So when we insert the 6, we would need to rebalance, but we would need to rebalance before then.
With the 5.
Yeah, exactly. Awesome. Okay. Cool. And then, all right, so let's move on to red black trees. So before we do this, I did want to make sure I gave you guys the attendance discussion really quickly. We don't have much time, so hopefully we can get through everything I think we can. But for the attendance discussion, I have a question for you guys. We don't color ABL trees, but if we did, what color would we color them? AV yellow. So that's the attendance discussion. A pass rate is just AV yellow, all lowercase, all lowercase. And for red black trees, it can come up. But for red black trees, the only thing we expect you to know about red black trees are basically these. Like there's not, you don't have to code them because trust me, it's a lot of work. But they are really helpful. So red black trees are an alternative to ABL trees because they're also a type of balanced binary search tree, but it just follows these 4 rules. Every node is red or black. The root's always black. A red node always has black children, so you never have 2 red nodes in a row. And null at the end, like if you reach the end of the tree, you just consider it black. And the number of black nodes in any path from root to leaf is the same. So for any path you take, starting at the root and ending at a leaf, always go through the same number of black nodes. That's what the fourth one is saying. And the third one is saying, yeah, just if you have a red node, like you can't have two red nodes in a row. Second one, just the root's always black, and the first one is a node has two colors. So we have a Menti question here on the next slide, but I think we'll kind of just go over it together because it's just a summary of this. But yeah, applications. So scheduling algorithms are helpful. Also, it's what you use for a C++ map. Actually, a C++ ordered map is just a red black tree. So that's pretty cool. Yeah, so red black tree is very helpful. And they have some advantages over APL trees. Discuss in a second. But this question again, we'll go over it together. Which of these are true? Well, it's what we just said on the last slide, right? It's a node is either red or black. Yep. Third is always red. That's not true, right? It's third is always black. And the number of black nodes on any custom rich leaf is always the same. That is true. And then this one, that's not true. Maybe it is. I don't know. But yeah, if a node is black, its children must be black. Well, that's not true because that means that every node has to be black because the root is black, but that's not true, right? So it's that if a node is red, its children must be. So only A is. Yeah. So moving on to the next slide, we're going to talk about splay trees next. So splay trees are just another type of tree. We don't go into a lot of detail on this class about splay trees, but they can be pretty helpful for like caching and stuff because they're self-balancing binary search tree. But the interesting thing about them is that after a node is accessed, it moves to the root via zigzag rotation. So after you access a node, it's always going to be the root the next time. So if you're accessing one thing a lot, that's good because it doesn't take as much time to find it. So we can kind of see that here, right? You actually access, I guess, the one, right? So if you access the one, it's going to move up towards the root. And then you have a balanced tree. And it ensures that most commonly access bins have access time. Okay, we'll talk about B trees in a second. I did want to go back really quickly because we didn't talk about the difference between red, black, and APL. The main difference is that the nice thing about red, black trees, and this isn't something you have to know, I'll just mention it. The nice thing about red, black trees is that it guarantees, like, you know how for a deletion in an AVL tree, we have to do log n rotations possibly, but that's not true in red, black. Red, black ensures, like, I think it's 01 for both insertion. So that's it, or at least it's fewer. Yeah. Okay. But for B trees, so B trees we'll go into a little more detail on, and also B plus trees, which are very closely related. So we'll talk with them. We're not going to ask you to like implement them in this class, but you do need to understand them. So let's look at something. So they're a type of self-balancing binary search tree, and they're used for key value storage. So they store huge amounts of data for fast query and retrieval. It's an n-array tree where each node has up to n children, and they can have multiple key value pairs in a node, sorted into something like keys. So what that's going to look like is you have something like this. You have this on the left is a B tree, order 4. And so what it is like each node can have, I think at most n-1 children, except you could have, or yeah, each node can have at most n-1 children, and at the least you could have like n keys. Okay, and on the right we have another example of a B tree. But the rules actually we discuss more on the next slide. But this is just a quick overview of B trees. Oops. Okay, so now properties. So yeah, all nodes have at most n children, and the root is either a leaf or has 2 to n children. And then internal or non-leaf nodes have ceiling of n/2 to n children, and non-leaf for internal nodes have a maximum of n-1 keys. L is the maximum number of keys, right? So I'll go over kind of what's important to know about this. So the first thing I want to go over is actually an example. So if the way B trees kind of work, let's go over that. I think that's important to know. So if I have a B tree, right? Like these are good properties to know, but like let's go over like more specific stuff because this is just a lot of like random information. So let's say I give you a B tree that looks like this. And notice that in a B tree, each node has like multiple values. And actually, interestingly, a lot of times B trees, those nodes are implemented with red-black trees. You have to well, quickly find things within each node. So just interesting. But anyway, let's say we have something like this. And let's say each node can only fit 2 things. So let's say we have like, I don't know, 5, 15. And then in the middle, we have like 10, 13. On the left, we're gonna have like 2, and on the right, we're gonna have 20, 25. So to go over this example, let's say that I want to insert 3 into the feature, right? If I insert a 3, what's going to happen is we're going to go to the root, right? And we're going to say, okay, well, is it less than 5? If it is, it's going to go into the left tree. If it's greater than 5, but less than 15, it's going to the middle one. When it's greater than 15, it'll go to the right one. But it's less than 5, right? So it's going to go into this one. We're going to put it in the right position in order, right? Well, 2 is greater than 3, so put it after. Okay, so you inserted 3. But notice the whole thing is full now. So if we try and insert something else, it's going to become a little bit harder to do. So let's say we try and insert, I don't know, 14. On inserting 14, the way this works is we insert 14, and this is for insertion into a B tree. So it's not in the slides, but I think, yeah, this is definitely something that's good to know. So that's why I'm going over it. So I guess, yeah, try and pay some attention to this because it's not in the slides, but okay, hopefully you guys know how to do it. So if I insert a 14 into this B tree, right, it's in between 5 and 13. So it's going to go into the middle node, right, into this one. And the way it works is it's going to go, well, it's larger than 10, larger than 13, so the 14 is going to go here. We don't have room for it because the most number of nodes we can actually fit into here is 2. So when you don't have room for something in a B tree, the way it works is it takes the middle element and it moves it up. So what it's going to look like after this is, so far, this 13 is going to be moved up, and the 14 is going to be put there, right? Because it moves the middle one up, and that's it. So it moves the middle one up, so now 13 is going to be put into here. So when we put 13 into there, we have 5, 13 is between 5 and 13. So 13 is going to go here, right? So we have 5, 13, 15. But there's a problem. What's the problem with this root, at the root? Well, it's overfilled, right? Just like I mentioned before, if each node can only have 2 values, right? This one's also overfilled. So what's going to happen next is it's going to take this 13 and it's going to move it up. So this 13, right, is going to be moved up because it's the middle value. So you always take the middle value, and if it's full, you always take the middle value and move it. So, well, the 13 has to be moved up. We have 13. And so this is kind of what it's going to look like. Okay. And yeah. So for a B tree, when you insert something that's overfull, you move the middle element up until you don't have overfull nodes anymore. And sometimes that means increasing the height of the tree, as we saw here. The height of the tree was 2 before we inserted, and now it's 3. So that's just something that's like kind of good to be able to follow along with. Does everyone follow that? Okay. Good. Cool. Right. So the next slide, we're going to talk a little more about B trees. Or okay, B trees and B plus trees. So B plus trees are very, very, very similar to B trees. There's a couple distinctions. So for B trees and B plus trees, so a B plus tree is basically a B tree, but there are some differences. So each node contains only keys. And we're like, okay, what's the difference between key and a value? Is that, so basically the only data we care about, like the actual values in the tree, B tree are every single value is both a key and a value. So everything's like unique in the tree. So, but in a B plus tree, the only values we actually care about are at the leaves. And these ones that are internal nodes, at internal nodes.
Right before test 2. Like, fuck me, bro.
Okay. And for B plus trees, right? The internal nodes have no actual value. They just are there to tell you which way to go. So like in this B plus tree, the only elements that have actually been inserted into the tree are 1, 3, 4, 5, 6, 10, 12, 15, 16, 18, 20, 25. These elements here are not actual values in the tree. They're just there as like placeholders to tell you whether they go left or right at each place. Like if I wanted to find the 1, the way I'd find the 1 is I'd go to 6 and I'd say, okay, less than 6, okay, less than 5, so it's in this one. But this 6 here is just there to help you find your way. Whereas in a B tree, it also is a value. So in a B tree, this 10 has actual meaning. It's an actual value in the tree. But in a B plus tree, the only values we actually care about are at the leaves. Okay, so that's what that means. So all data is actually stored in the leaves. And
Right, but this is 6, 5.
those are nodes, right? And they may those numbers may or may not be actual data. Yeah, like the actual data that we care about in a B plus tree is only the leaves. In a B tree, everything. So an additional level is added at the bottom with linked leaves. So all the leaves are linked together in a B plus tree, but not in a B tree. So we're running a little low on time. Sorry about that. I'll try and speed up a little, but let's just go over some examples of how to calculate things really quickly, because I think that's important. So why use B trees? Well, external blocks, so like caching and indexing of file systems. Okay. So we're going to go over this one together and the next slide together. So these are Menti questions, but I think it's important you guys know how to do them. So I'm going to go over them with you. Oh, okay. But this one, which of these is a B tree, which is a B plus tree? Actually, do any of you know this one actually? Yeah, exactly. Right. And we know that because
Because of the last one.
yeah, the last level, everything's linked together. And also in a B tree, you're not going to see like duplicated values because in a B tree, because everything is like both a value and like a node. But in a B plus tree, you might see duplicated values but not in the leaves, because like this one here isn't an actual value, but this one is. So things might appear more than once, but this one doesn't have the meaning this one does. Okay, so question 9. So these two questions we're going to go over because they are kind of important. So if you're given a perfect B plus tree with n equals 3 and L equals 3 and height of 2, how many unique keys are there? So the way we calculate this one is like this. We can kind of draw it out. So I'm going to suggest that you guys do this. So you have height of 2, right? So level 0, 1, and 2 is a perfect B plus tree. So what that means is that, and with n equals 3 and L equals 3. So at the root, right, we have 3 things. Or it doesn't really matter how many things we have, but it can have up to 3 children. So it's going to have 3 children, right? And so then these 3 children are like this, and each of them have 3 children. Okay. And the reason why they each have 3 children, I guess actually there are only 2 values here. So these, like, forget that these are all 2 values, but because they're internal nodes only have up to n minus 1. But the main takeaway here is that for a B plus tree, right, it's 3, 3, 3, right? And each of these have 3 children, right? And so on. And at a leaf, right, you can have n equals 3 values. In an internal node, you can only have n minus 1 values. So in internal nodes, I drew 3 here, but it should only be like 1 bar, so 2 things. But in a B plus tree, where are all the values stored? Right, the last level. So for a B plus tree, the number of unique values that we're counting is only the number of values at the last level. Well, how many like of these like little ovals are there? None, right. And how many values can they each hold? 3, right, exactly. We get that from n equals 3. So the number of unique values is n times the number of ovals at the bottom, 9, 3, 27. So that's for a B plus tree. Yeah, I think it's number of yeah, all leaf nodes have a maximum of L keys. It's the number of keys that the leaves. But internal nodes have n minus 1 key. Yes, so that's how we got this 3 actually. It was not from N, sorry, it was from L. Yes. Sorry. So sorry, L is 3 because L is the number of like values each leaf has. So that's the 3. The 9 here comes from the fact that it's the number of like leaves there are. And we get that from the fact that like the first level has 3 children. The second level, each of those 3 children has 3 children. So at the leaf, there are 9 leaves, each with 3 values. Okay. And I see a message. So yeah, I'm sorry I'm running a little long, but I'm gonna try and finish. Okay. I would always be L to the power of N. So not quite because the height matters too. So well, I guess yeah, all nodes have most N children. So not quite because yeah, it does matter the height.
Is it L times N to the power of the height? Is that like, is there like a formula, I guess, to calculate how many nodes each time?
I think that might actually be right. Yeah, for a perfect one. The way I do it though is I kind of just draw it out. But for next, we're also going to talk about what it is for a B tree. We see this one's 27, and hopefully the next example covers even more because B tree is going to be similar, a little bit different. So we're going to see visualization here, 2, and each of these have 2 keys is n-1 for an internal node. And then each of those have 3. And so they're focused. Okay. But now for a B tree, it's a little bit different. And we'll go over this one kind of quickly. It's already over on time. But it's the same thing. N equals 3, L equals 3, height is 2. So again, we're going to draw it. Internal nodes have n-1 keys. So 2 keys, right? And we have n equals 3, right? So each of these, if it's perfect, it's going to have 3 children. So we have 3 children here. Each of those is an internal node. And internal nodes also have just 2. Each of these is going to have a leaf node, or 3 leaf nodes, right? And each of those has 3, because we can have L equals 3 leaves. Okay, and then it's going to be the same for these 2. So just like before, at the bottom level, how many values do we have? Oh, yeah, we have 9 leaves, but yeah, 27 values. So 27 values. But it's a B tree, so what else do we care about? Yeah, that's right, we care about the other levels as well. And so at the other levels, how many values are there? Yeah, right, two each, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. So it's 27 plus 8. We have 35. That's how we calculate. Does that make sense right now? Oh yeah. So n equals 3, right? What that's telling us is that well, as is here, max n children. So each node is going to have, if it's perfect, each node has n children. And each internal node is going to have n-1 keys. And then each leaf node has L keys. Oh, sorry. Each leaf has L keys. Each internal node has n-1 keys. Each leaf has L number of keys. But internal nodes have n-1 keys. Yeah, right. Anything that's not a leaf is an internal node.
How did they like specify what like the middle one is, I guess, is like necessarily connected to? Because like, if it only has like 2 keys, but then has 3 nodes like connecting from it, like is it necessarily like, pointing to anything, or is it how is that stored, I guess?
So yeah, that's a good question. But usually, I hope that's not a question. I think I know what you're asking. So usually for like a B tree, the way it works is like those 2 values, you have like you're gonna have pointers. So pointer is something that's like less than the smaller one. Pointer is some like a node in which everything is in between the 2, and a pointer to something that's larger than both.
Okay, so numbers that are in between the left and the right window.
Yes.
Okay.
Yes. hopefully, yes, all that you can maybe work it out on your own a little bit. I did want to briefly go over one of the coding questions we have. Well, we don't have a lot of time for it, so it's already over. So I'm going to try my best to go over it. Hopefully, this makes sense. And you guys can look at a visualization. It's visual, but here's visualization because these are tricky. So I suggest that you, if you aren't really following, maybe like just start putting numbers into here and see if it kind of starts making some sense. Okay, I see some more things in the chat. Oh, it's not 20 yet. Okay, cool. Yeah, it might, Kyla might actually do that. But anyway, so yeah, so this is good to know, but let's just quickly go over this coding question. I don't think we have time to go over the last week's coding question, so sorry about that. We'll go over this coding question with you. I'll try and speed up next week more. But you're presented with a perfect binary tree. Node pointer looks like this. You have an int value, left, right, and next. But for the next pointer, what we want to do is we wanted to point to the next thing in the level. So for example, for this one, we have 1, 2, 3. We want the 2 next to be 3. Even though it's not next to it, we want it to be the next thing over in the level. Does the question make sense? Okay. So you have an idea of how we might be able to do this? Yeah, which types of traversal would we be using? So for post order, that would be, well, that's good. Yeah, this is a binary search tree, but
Oh, sorry.
that's good. Yes, actually, that's okay. This is a level order traversal because if we notice, we're basically just the next thing is the next thing in the level if we're going level order traversal, right? Like 1, 2, 3, 4, 5, 6, 7. That's a level order traversal, right? And the way we're assigning the next node is we're just assigning it to the next thing in a level, like going to the right. So the way we would do this is actually with a level order traversal. So let's look at the code for it. We'll talk about it, and then that'll be it for this week. So yeah. So we're going to use a level order traversal. So the trick here is that we're saying the current pointer is next to no pointer. If I okay, so for a level order traversal, we use a queue. So if the root is not null, basically, then we push the root, right? And while our queue is not empty, so while we haven't gone and seen every element so far, for each level, we're going to go through how many things are in this level. We're going to remove the thing from the queue and add its children to the queue. But importantly, we're going to make the next pointer point to the next thing in the queue, right? So current is the current thing in the queue. Its next is going to be the next thing in the queue, right? Queued up front. But if it's at the end of the level, so if I is equal to count minus 1, his count, remember, was the number of things at this level. So if I is equal to count minus 1, we set the next to null pointer. Because what that's saying is like if we're at the end of the level, the next thing over is null. Oh, sorry. So the code for the discussion is AV. Okay. And so that's about it. And then we just go through every level and do that. Hopefully that makes sense. It's great over. You guys can look more at the code if you'd like. Later. And questions, and then here's some resources. I guess I'll go over the quiz question from last week like really fast. But I guess I'll just talk about more of the approach. Do you guys know? Were you guys able to kind of have an idea of how to figure this out? Okay, if not, that's like okay. It's very similar actually to this code, because in this code we did a level order traversal. In this one, it was the same. What do you think the difference was with the quiz question? Yeah, that was a possibility, I think. Something like that, yeah. But also, I think the main difference here was that you only were taking the sum of a particular level, right? So you would do a level order traversal for all levels, but you also have to keep track of which level you're on. So this, as we notice, this code's very similar, going until it's empty rather. And yeah, the difference was from this previous code, which we just saw, was this statement right here, if L equals level. So if we actually reached the level we're looking for, we start adding to the sum. And that's it. Okay, but otherwise, it's pretty much the same as the level large reversal. So the large reversal for both problems is the weight zone. I wish I had a little more time to go over this, but actually, yeah, I have an empty queue. If there is an empty, chance the queue. For each level, get the size of the queue and loop through the size of the queue, because that's how many things are going to be at that level. Add the values together at the front of the queue, add the left and right children of the queue, and then pop off the queue. And then when you actually reach the level you're looking for, start adding to the sum. That's all. Okay. So you could absolutely use recursive for this one. In fact, there was a TA who wrote a recursive solution. We just decided, and recursive is a lot shorter. The reason why we are showing this one is because I think readability is a lot. But yeah, you could absolutely use. Start running level 1 too. Oh, awesome. Okay. But yeah, that's it. So, thank you all, everyone. Good luck.
Thank you.
Yeah.